So the last we were talking about a continuous case. We'll give a very nice sort of a elegant yet simple case that people has been actively working on, called Cournot Duopoly case. So think about that. You have you are ISP provide service, internet service to the market, competitive market. You have a common one market with a single price. What you can do? You want to produce more service, or in other words, the bandwidth, or not? I mean, this is not the idea situation, but idea case to really demonstrate this Cournot model. But there's a various of other cases can be modeled by Cournot model. But for the moment, we're just thinking about that you got these multiple forms indexed by I, then each of them produce their a quantity amount of their products as the number n, okay, and produce that, then there's a cost. So n is the number of these ISPs. So then given a particular ISP I, then you can produce the amount of the product which is indexed by Qi. And the C function is basically the cost of you produce that quantity of products. And those total quantity in the market would determine the single price in the market price, which is function of P. So there would be decreasing function because that you have a large quantity in the market, therefore the price is going to go down. Then each individual ISP agent, they are profit optimizer. So they're basically looking at revenue, which is the amount of the product produced multiplied by the price on the market. This is the revenue, and minus the cost, which is the cost multiplied by the basically the cost. So then you can write it down, the payoff function or the reward for each of these agents, for each of the four, let's say. And the goal of them really try to sort of maximize this. But you can see this is a game, because if you try to produce the bandwidth, right, Qi, then obviously the price would have an impact, also would be influenced by the amount from other players. You got n number of players. Then therefore your payoff is determined by other actions, by the action from other players. So you can think about this sort of it's a game, but the action space is not finite, but is rather a continuous variable. So we could come in with a linear function, like for example, the P we define is the linear function, a decreasing linear function, invert demand function. And we also can define the C as linear as well. So you can write it down, this function, as a quadratic. When I say quadratic, is respect to the action Qi for each of the player. And then we're looking at this Nash equilibrium definition. Is that nobody wants, suppose in the optimal space, nobody wants to defray from it. And we can using this maximum sort of equation and to, looking at the first order condition. In other words, we take a derivative, the derivative has to be 0, isn't it? Because the quadratic function, and so the convex, therefore, a convex, therefore, a concave actually, then therefore, you could find take the derivative, you have two equations. You have two variables equation, therefore you can solve that problem. So the solution is basically a minus c and divided by 3. So that's the quantity you can find. So So this is sort of result. We will illustrate to try to make sense of it. You can also think about the best response, right? Remember, we have this best response correspondent. So in this case, it's actually best response function. You only have one solution rather than multiple best response. So in this case, and you can write it down, you know, the best response Q1. So in other words, this best response, the player one's best response towards to player two. Let's looking at the two agent case, and best response from player two to player one. And those best response can be, plot by looking at these action space, because you have best response, you can write it down. So if you were taking Q2, what would be my Q1 look like? So you can write it down, the best response. And think about this, that the only have one cross between them. So this is sort of a Nash equilibrium, isn't it? Any reason why this could be the Nash equilibrium? Would anyone can answer that? You could speak if you want.
Because neither ISB would unilaterally change their action because they have the optimal for the other one and vice versa. So it's the fixed point.
Yes. So your best one is to me, I'm best one to you. Therefore, the only solution in that case is a cross between the two lines, which is Nash equilibrium. Let's do analysis to see what happens. So let's compare to some of the cases. Let's say the case that one SP, suppose given everything, they say, okay, I'm going to dominate the market. This Q2, you are not allowed to produce anything. Q2 is equal to 0. So in this case, your solution would be here, right? And there you would, as one dictator on this, you would produce this amount of quantity, which is, obviously more than this in the Nash equilibrium. So because of this duopoly, and therefore the quantity, the amount of the product produced would be smaller than A minus 2, A minus 2 divided by 2. So that it would be smaller than that. So that's basically this impact from the other players, other firms, because they produce that product, therefore drive the price down, and therefore you're not gonna keep increase your quantity, right? Until you increase a certain level, and then you don't want to increase anymore. So yes. And then we can looking at other cases. Suppose that so the aggregate profit for the duopoly would be maximized by setting Q1, Q2 equal to Qm divided by 2, A as 4 in the half of the monopoly quantity. However, because Q1, Q2 is lower, each has yes. So suppose that you think about you as globally optimize it. So in other words, that suppose you are think about as God, right? I want to maximize the overall product of U2. And you can find that if you do that, consider as a single agent, but you try to maximize Q1 plus Q2, let's say, just looking at social welfare as we discussed. Then you will end up with this solution, which is effectively each of the players would have this quantity is A minus C divided by 4. So what this means is basically somewhere here, somewhere here. Sorry, basically somewhere here. And then this is actually optimal socially. But then in this duopoly cases, that if they decide make their decision by their own, and they have incentive to deviate from this, and sort of move gradually from this until here, reach here, and then it's a natural equilibrium. They don't want to move anymore. So in this case, you can think about that. This is a Nash equilibrium, right? And this is sort of say, if you try to dominate the market, can allow other people don't produce, and that's what you can produce. And this is something considered social ones, and then this is basically each agent play selfishly what happened. So from here, the quantity, you can see that products increases is simply because the selfishness of individual agent. You can see that a lot of phenomena like this called I don't know, there's a common grass, tragedy of commons. There's the idea that you have a common ground for people to sort of graze their, let's say, stocks. And you can find that people tend to sort of over farming that kind of common resources. So equally here, the common resources can think about as a, the common market has a common price, can drive the price down, then the socially beneficial for everybody. So basically they harm themselves, not only harm others, but also harm themselves because of that. So I think this Cournot model, it's very simple, but it's very profound theory behind this sort of game theory. So just looking at the last bit about the learning, I think we've been spent a few hours about this game theory, but people might ask, what is to do with multi-agent AI? What is to do with machine learning? What is how can we really see this? We're going to obviously talk about this for the following lectures, but just want to give you a taste of it to really see, oh, this is sort of a learning plays role here. So think about this as a, best response. So in other words, let's say in the very beginning, we don't really know the solution in the Nash equilibrium, right? We don't really know whether they are stable just yet, but allow the form to react based on this opponent's decision. Okay, we allow them to have a chance to sort of introspective, and also allow them to really fetch the data to see what happens. And during this process, you can actually adjust their, produce the Q, let's say, and see what's gonna happen. So let's say in the very beginning, they started with a random production, Q, let's say Q, Q0 somewhere here. And because they know all the information, therefore they know, their best response. So for example, so R1 is the agent's firm one's best response given the value of Q2, right? So this is basically Q2's value. Let's say in this case, this is Q2's value. My best response, because obviously best response is that I'm going to maximize given, let's say, the opponent Q2 play this much of, produce this amount of product. Then I'm going to maximize my sort of, utility. Therefore, I will reach here. In other words, this Q1, 2. So the Q11. This one here, upper script is really talking about the time steps. So then I'm going to update my production in term t, in term 1, so that the quantity is my best response towards to Q2 at term step 0. So equally, this Q2, right? This player 2 also do the same thing, and this is their response curve, right? And therefore, this is amount they should produce optimally. So I would actually write down Q2 1, update in step 2, right? If you do that, these two are moved to, because of this, right? You basically move to here, isn't it? You basically move to here. So this is basically the Q. Let's write it as a vector. If you write a joint sort of a joint amount that is produced from these two agents. And so this is basically 1. So you can see that actually towards to this. And after a few iterations, they will actually reach to this equilibrium. So that's one of the sort of justification or interpretation of Nash equilibrium, is that if they looking at the opponent's action and do the best response, and eventually, in some cases, eventually it will come to the equilibrium and nobody want to deviate from it. So this learning type of adjustment process, and we will formally introduce about learning and have some sort of element taste of learning, because they observe the data and based on opponent's behavior, I do the change and eventually I become stable. Do we have any questions? Any question? I'm gonna looking at this chat. Does this iterative process always work? What happens if the equilibrium is not stable? Yes. So very good question. And the machine learning about the multi-agents, they are all about this, right? Whether this learning would work, right? Eventually would, number one, the question would ask is that whether they're going to converge, right? What are the points they're going to converge to? Whether this convergence is stable, in what situation it will be stable. Okay, so let's take into this particular example. In this trivial case, one can prove, in fact, it is stable in the sense that if you initially running random initialization starting point, they will always converge to the Nash equilibrium. And there's a bunch of paper, in fact, after Cournot's model, I think it's from 60s and so on and so forth, really talking about stability, convergency, stability, and so on and so forth about this. So I think this is actually something to do with dynamic system, right? I mean, if you're familiar with the dynamic system, and you can actually model this process as a dynamics governed by the dynamics, and you can looking at this eigenvalue of that dynamic function, and then choose some property really about that. But bear with me, and we're actually going to talk about that in our literature, in our lecture, and in some of the cases we can actually show indeed it will converge. So just understand the concept that in this particular case, in fact, the underlying rationale behind we do this best response is that we would expect that the opponent would always do the same. In other words, they output in the future going to be the same as this. Otherwise, what's the point of what do best response, right? But precisely because that that's not always they will converge to equilibrium, right? In some of cases, it's not really stable, and in some of cases that there's a circling effect. Then there's no guarantee it would converge. And so despite of that, and the people based on this sort of iteration, coming with more sort of a, rigorous sort of a learning algorithm called a fixtures play, which we're gonna touch upon later. So bearing in mind this process, best with one process, and then we have this, later on people develop this fixtures play, which we're gonna introduce, and also the gradient update as well. You don't need to update best with one, but you update gradient, and think about the back propagation in the neural network. And also, this is in this particular case is globally stable because at any starting point you will convert to Nash equilibrium. We can obviously talk about the property like unsymbolically whether it's stable, right? In some cases, it is the case that you might have initialized close to, one of Nash equilibrium. Sorry, one of Nash equilibria. Then therefore you would convert to that kind of Nash equilibrium. So in the multiple Nash equilibria case, so in some of the Nash equilibrium point, it's a stable, symbolically stable, because any point close to it will converge to it. But you might have other Nash in equilibria, they don't. So this sort of opened that whole series of study on that. But of course, this module is still a very beginning of this. So I think I can obviously provide this various of analysis on that. And then there's a rich literature behind it. And also important thing is that it also ignores that the current action will have influence on their opponent's action in the next period. In other words, we not really consider that when you're taking this action, to harm other people, and the other people will remember that. So, so in the repeated game, we're gonna examine a case that they're gonna face each other repeatedly. In other words, they got the same, players, but play this game many, many times, and we're gonna looking at is accumulated reward from those plays. So if that's the case, then they actually have a different Nash equilibrium, right? And then this kind of argument about play convert to Nash equilibrium probably wouldn't play that valid anymore. But there's two different situations. Is that you got this long-term kind of reward given your current action, but you on a base but you're gonna optimize long-term accumulated reward. So in that case, it's repeated again, Markov decision process and so on and so forth. But this, update fixtures play is really about learning of one short game. But you have opportunity to sample the data, observation. Once you have observation, then you can actually drive your solution to the optimal ones. So they are actually two different, they are subtle different, but they are actually two different concepts. But the key difference here, mathematically, is the discount value. The discount value, whether when you're taking action now, you're going to discount the future action you're going to have. So the future action, future reward you're going to have in the future. And that discount value, if you don't consider the future at all, then this update would make sense. But if you're taking into account the future, maybe they will converge to different equilibrium. I'm not sure whether I can have made that clear, but we will repeat again in a minute. I list the references. I sort of clean up a bit. I have most relevant ones. So this is easy to understand game theory literature book. This is as well, but this have a other context, give a lot of application. So if application driven, go for this. If it's a basic math driven, this. If you want to do really research on game theory and really want to understand in depth about game theory, this is the one you should go. Okay, and so these other are some of the sort of lecture notes that I based on. I think it's very good sort of slides. Some from MIT, I think this is a very good one. Talking about game theory. It's one of the online course about game theory. Slides I think very useful. And yeah, some of this sort of a proof of Nash that I based on, and this is the original Nash paper.